All right, so since we're studying fluids, we're going to have to talk about pressure and different ways of which we can measure pressure. So pressure is defined as force per unit area. So how much force is applied to a certain given area. And therefore the units are force, newtons, per area, which would be in base SI units, meters squared. But we give that its own unit, we call it a Pascal, right? Which you would write as capital P and lowercase a. So the SI units for pressure are pascals. Although I'm sure you're more familiar with other measurement units for pressure. Some other examples are PSI, so pounds per square inch. Those are imperial units, but we're probably used to that with things like tires. Millimeters of mercury is another one, and atmospheres is another one. Okay, so you might be familiar with some or most of those ones. But let's try and do a practice problem with our new equation first. And with our new equation, we can make a triangle for it. So if it helps, here's our equation. Pressure equals force over area. But we can write it as force equals pressure times area, like that. So let's look at the first question. First question says a crate is 2 meters long and 1 meter wide. So here we have a crate. It's 2 meters long and 1 meter wide. The weight of the crate is this. So this is the force of gravity acting on the crate, which is the weight. What pressure does the crate exert on the floor? Okay, so pressure, we don't have to rearrange this equation. Pressure is force over area, but we do need to calculate the area. So in this case, the area is of a rectangle, which is just length times width, or 2 times 1, which gives us, well, 2 times 1 is just 2 meters squared. Okay, the units would be meters squared. You have meters times meter. So your pressure then is the force, which is given here, 5.2 times 10 to the 3 newtons, divided by our area, 2 meters squared. And that gives us a pressure of 2.6 times 10 to the power of 3, or 2,600 newtons per meter squared, or pascals. Now, 1 Pascal really is a small amount. This paper is probably exerting a force of 1 Pascal on the table underneath it. So 1 Pascal is very, very small. So typically, we don't use pascals, we use kilopascals, right? Which is 1 kilopascal is 1,000 pascals. So we can say this is the same as 2.6 kilopascals. And you can already see it's a much easier number to work with. Can you just pause there? So getting back to our PowerPoint, atmospheric pressure was one of the other ones I mentioned. And it's a useful one we use because it is basically the weight of the air above you. So there is a lot of pressure being exerted on you right now. And because there's a whole bunch of weight above you. All that air going from you to the very top of the atmosphere is sitting on top of your head. And all that weight over that unit, base unit area on a normal day, we say is 1 atmosphere. And 1 atmosphere is equivalent to 101.3 kilopascals. Right? And that's important. Atmosphere is very, very important in physics and chemistry. I mean, for example, we all know water boils at 100 degrees, but water boils at 100 degrees at 1 atmosphere. If you were to climb up to the top of Mount Everest, the pressure would be slightly lower than 1 atmosphere, and water would actually boil at a lower temperature. And if you were to keep going right into outer space, well, water would instantly boil. And that's the reason why we need spacesuits, right? It's not just because we need oxygen, right? If all we needed was oxygen, you could just have a mask and you can go into space. That's not all we need. Because if you just had a mask, sure, you can breathe oxygen, but you don't have the pressure put on your whole body, right? And so your blood would boil. It would also freeze because it's extremely cold out there, around minus 271 degrees. So it would boil and freeze. So you need that big suit because you need a whole bunch of air pumped into it so that you get enough pressure on your body. I think a human body needs at least 1/3 atmosphere. So suits need to provide at least that much atmosphere, that much pressure on your body, which is why they can be so hard to move around in. So moving on. So here's an example. This is a drinking straw. It's a wonderful picture. So you drink from the straw, and when you drink from the straw, you create a low pressure area. Now, around the straw, you have atmospheric pressure, which will be higher than the low pressure area. And things move, if you remember from chemistry or earlier sciences, things move from high pressure to low pressure. And so that'll push the liquid down, the water, and off the straw. Okay. This is also, like I said, when you go up to Mount Everest, there's less pressure. Even if you've never climbed Mount Everest, which I've never done, nor do I plan to, but I've been on a plane before. And a plane will take you up pretty high. And because you're at higher altitudes, there's less pressure around you than there is actually in your ears. So in your ears, you have slightly higher pressure, which is why it feels like your ears want to pop. Okay? Same thing will happen if you go scuba diving, just at a faster rate because water is a lot heavier than air. And so you need to be very careful with how you breathe with your lungs, right? You don't want to hold your breath as you're going up or down in water. That can be very, very dangerous. It's also the reason why if you go scuba diving, you wouldn't have a snorkel that's like 10 meters long. I hear some people, or maybe even as kids too, you always think, why are snorkels so short? I want them to be really long so I can dive down. It's because of the pressure difference. If you start breathing air from the pressure that exists all the way up there, compared to the pressure that is on you, your lungs could collapse. So you don't want a snorkel that is 5 or 10 meters long. Even if you think you can make one, don't do it. It will literally kill you if you try to use it. All right, so measuring that pressure. We've talked about that pressure above your head, or the pressure of any static pressure. We call it a static pressure, which is the pressure of a static fluid in a column above a point. Okay, so that amount of pressure is, well, it depends what it is. Like I said, air, water. Water is a lot heavier because it's more dense. So the density is important. So we have D for density. Okay? And then how high, like how much is it? Like from atmospheric pressure, the atmosphere goes up around 100 kilometers. Okay? So you need to know how high that column is. And then, of course, gravity. Right? How much force is being pulled down on you. So you need to know that gravitational field strength. So the equation is, for a static pressure head, is dHg. All right, so different ways of measuring pressure. This is a Mercury Barometer. Okay, so here we have a tube. Okay, at the top of the tube, we have a vacuum, and the bottom is open and stuck inside a little pool of mercury there. Now, atmospheric pressure pushes down on the mercury around the outside of that tube, which causes mercury to rise and be pushed up. The more it's pushed up, the higher your static pressure head is inside of that tube. Now for mercury, if you're doing this at atmospheric pressure, mercury will raise 760 millimeters until that pressure caused by this static pressure head of mercury is equal to that of the outside atmospheric pressure. And so we say 1 atmospheric pressure is the same as 760 millimeters of mercury. And of course, if you somehow increase the pressure, it'll go higher. If you can decrease the pressure, it'll go lower. So that's one way of measuring pressure, which is why this has been used quite often, which is why millimeters of mercury is a common unit for pressure. Also, I have one of these, so when you're in class with me, if you want to see it, I can show you this. But if you have all these different shapes and you pour water, water will go to the exact same level, right? It wants to sort of equalize the pressure among it. It's not going to go higher for one than the other, because then the amount of pressure is different, right? And if this pressure is higher, it'll push down on this one until it levels. Okay, this is why we often hear the phrase, water seeks its own level, which is also why a siphon will work. So water will actually go up and seem to sort of raise up a siphon just so it can get to a lower level. Of course, the siphon wouldn't work if you actually had this portion lift higher. Then in that case, it's not going to work. Water wants to seek out the lower level. Okay, so if you're doing a siphon, that needs to be at the lowest level. Next thing, this is called a nanometer. So if you have the exact same pressure on both sides, so just holding it and you have atmospheric pressure on both sides, then it'll sort of equalize, right? Just like this example here. However, if you put some sort of pressure on one side, the other side will rise. Now the other side again has atmospheric pressure on it, and this has some sort of absolute pressure that you exert on it in some form. And the difference between the two that this makes is called gauge pressure. So you can say gauge pressure would be absolute pressure minus atmospheric pressure. Okay, so gauge is just the difference between the two. Let me just pause there before we do some practice problems, see if anyone has any questions. All right, so I'm talking a lot about pressure. Let's try this practice problem. Question number 2. So we have pressure is applied to one end of a water manometer so that the difference between the two heights is 10 centimeters. So from here to here, that difference is 10 centimeters. First, what is the gauge pressure? Well, you can think of the gauge pressure. It is the difference between the two, but because we know the height of this column here, we just look at the column from here to here. That's gauge pressure. So we can calculate it just as a static pressure head. And we have the equation for that. So we'll say gauge pressure, in this case, is a static pressure head, which is the density of whatever that liquid is. It's water, so we know the density, times the height, which is 10 centimeters, times gravity. Now, if you don't know the density of water, I'm going to tell you right now, it's 1,000 kilograms per meter cubed. That's the density of water. Times by the height, which is 10 centimeters, but we want this in our base SI units, which would be 0.1 meters, times by gravity, which is 9.8. I'm not going out of space here. Okay, so when we put that onto our calculators, we get 980 pascals, or I can write it as 0.98 kilopascals. 980 pascals, or 0.98 kilopascals. Right, so that's the gauge pressure in this case. Next it says, what's the absolute pressure? So this pressure right here that's being applied, what is that? Well, we know that gauge pressure is the difference between that absolute pressure and atmospheric pressure. Now I said atmospheric pressure is 1 atmosphere, but in kilopascals, 1 atmosphere is 101.3 kilopascals. That is what 1 atmosphere is in our SI units. Now since I'm using kilopascals here, I'll use the same here for gauge, which was 0.98 kilopascals. Okay, so now I just need to rearrange the equation. I can take this term, bring it to the other side, so I'm adding it to both sides. So you would get a positive 101.3 plus 0.98, which gives you an absolute pressure of 102.28 kilopascals. So that's your absolute pressure. Just pause there. Okay, and if you know the answer, as we go through this question, you can just type A, B, or C into the chat. That way I don't have to edit the video later. So, question 1. If the height of a column of fluid is increased, it will exert more pressure, less pressure, or the same pressure. So we increase the height of a fluid, column of fluid, so the static pressure hit. More, less. So think of it like this. If this was higher, would you get more pressure or less pressure? I got some B's and some A's. It's actually going to be more pressure. So let me try and explain why. So our equation is the pressure of a static pressure head is dHg. So if I had, say, this column and this column is a lot higher. There's more stuff above you if you're thinking of it in terms of atmosphere. Right? So if H is bigger, P must also be bigger. Okay? Question 2. If the width of a column is increased, it will exert more, less, or the same. I'll give you a hint. Look at the equation. Does width have anything to do with it? So A, B, or C? What do you think? Type into the chat. I don't see anyone typing. Okay, it's going to be C. It's going to be the same. Okay, it only changes based on the height. Okay, if you have more width, well, sure, you're going to have more stuff, but it's also exerted over a greater area, so those two kind of cancel. All right, in a mercury barometer, the higher the atmospheric pressure, the blank, the static pressure head. So is it the higher the static pressure head, the lower the static pressure head, or static pressure head will not change? So that static pressure head was, if I go back to the PowerPoint, right, it's this one right here. So the question says, if the atmospheric pressure is higher, so if this becomes greater, what will happen to this? Will it go up, go down, or stay the same? Okay, higher, lower, or not change. Alright, so I'm getting A's. Good. So it will go higher. A. Number 4. A siphon can be used to move a fluid to a higher point, a lower point, or whichever you want. Higher, lower, or whichever you want. B. Good. Has to always be at a lower point. Okay. Last question. If the atmospheric pressure is 100 kilopascals and the gauge pressure is 300, the absolute pressure is what? I'll give you a hint. You have to look at the equation. So gauge pressure, which is 300 in this case, equals absolute pressure minus atmosphere. So gauge is the difference between absolute and atmosphere. So if gauge is 300, then absolute and atmosphere needs to be 300 apart. So what would absolute be? 200, 300, 400. What makes this work? A, B, or C? You can try a guess and check if you're not sure. If you think it's 200, does 200 minus 100 equal 300? No. All right, well, what about 300? Would 300 minus 100 equal 300? No. How about 400? Does 400 minus 100 equal 300? Yes. Okay, so I'm going to stop there and see if anyone has questions.